Well, in the previous presentation, I talked a lot about concepts, as well as interpretations. And that is because the beauty as well as the relevance of multivariable calculus certainly comes from the fact that all these results are conceptual and can be interpreted in a physical way, and those physical interpretations ultimately lead to things such as predictions in electrodynamics, for example. Well, this presentation is going to turn all of that on its head, because here we're going to talk about computation. Take my word for it. And that is because the power of multivariable calculus all lies in the fact that we can compute things that ultimately can be interpreted and can predict reality. But that also means there are parts of calculus that are straight computation. After all, the word itself comes from calculating, and so that's what we will need to do here. And well, yeah, let's get started. We're talking about the multivariable chain rule, which will be relevant in terms of coordinate transformations, as we're even going to see at the end of this presentation, even though that is something that is more of an advanced topic. And the chain rule will also be very valuable for us to compute directional derivatives. So these calculations will be connected back to concepts in the very next presentation, but not in this one. All right, so let's take a look at what the chain rule needs to do. Basically, we know that quantities such as air pressure or temperature depend on a point's location in space and on time, because air pressure changes as we travel from one point to another, and of course it also changes in time. If we are now looking at the position of an object, such as an airplane, that depends on time. And a natural question to ask then is how the air pressure or the temperature at the location of an airplane varies in time, or from the point of view of differential calculus, we would want to know the rate of change. Now, certainly this is a visualization that I've cooked up just to try to explain to myself as well to others what we are doing with the chain rule, but there is certainly also a bit of industrial relevance here, because if pressure and temperature change too fast, you have different stresses on the fuselage of an airplane than you would have if they change more gradually. All right, so basically, if we just want to compute that straight up, it's not that bad, because we can obtain the pressure and temperature as a function of time by simply substituting the position of the airplane and the time into the air pressure / temperature function that is a function of 3 space and 1 time variable. And well, then the only thing we need is really that we need some type of chain rule to compute the derivative, because what did we always use when we plugged a function or something into something else? We used a chain rule. The thing here now is, of course, that we are plugging 4 functions into a function of 4 variables, in this example at least. So let's first take a look at that when we have an example of a function of 2 variables, and that function is f of xy equals e to the x plus y squared, and then 2 input functions, x of t equals cosine t and y of t equals t plus 1, and we want to compute the derivative of f of x of t, y of t with respect to t. Now, what I should say here is this is an introductory example. This is not how we're going to compute these derivatives in general, because it simply gets too complicated, because if we plug a lot of functions into something that's rather complicated, and these were chosen to be comparatively simple, well, if we do this with really complicated stuff, the expressions just get really big. Okay, so f of x of t, y of t, well, that would be e to the cosine t plus 1 quantity squared, right? Because t plus 1 goes in here for the y. Okay, so it's e to the x of t plus y of t squared, and that would be e to the cosine t plus 1 quantity squared, just like I said. If we now want to take the derivative with respect to time, well, the derivative of e to the cosine t plus 1 quantity squared, that'll be the derivative of the exponential, which is e to the cosine t, exponential comes back, times the derivative of the inside, which is negative sine of t, plus the derivative of t plus 1 squared, which is 2 times t plus 1, times the derivative of the inside, which happens to be 1 here. And of course, now we could also simplify that, but what I want us to realize here is that in this pattern, This part here is the derivative of the function with respect to x, and then we plug in x of t, y of t. So this is df dx. This here is the derivative of x with respect to t, so that's dx dt. This part here is the derivative of f with respect to y, and then we plug in x and y, so that is df dy. And the one here, of course, is just dy dt. And so what we can see here, and this is something that we're now going to establish in an abstract proof, is that the derivative of a multivariable function into which other functions are plugged in is computed by taking all the partials of the multivariable functions, just like we're taking df dx and df dy here, and then multiplying these partial derivatives with the derivatives of the corresponding input, dx dt and dy dt, where those derivatives, these quote-unquote inner derivatives, are then taken with respect to the variable that we want to differentiate the overall function to. Okay, something else that we need to get used to here is, as we are looking at functions of multiple variables, it'll be more and more common that we don't write down the arguments because it's simply too much to write. Now, this is something that is a bit of a change, of course, in calculus, but if you think about physics, for example, it is already very much common usage, because when a physicist talks about pressure, they write down P, they don't write down P of X, Y, Z, and T. So in many ways here, and that's also something that I'll probably say periodically and may have already said a few times, multivariable calculus is the confluence of calculus with physics, and that is very, very natural. Okay, so that example is done, so now let's look at this abstractly. The theorem is the multivariable chain rule, and I call this take one because actually the multivariable chain rule will have weaker hypotheses, but I want us to get through the abstract part and the computation here first with stronger hypotheses that are typically satisfied in applications. So if we have a function u of x1 through xn, which is a function of n variables, and we are going to assume that this function has continuous partial derivatives. So that is the hypothesis that ultimately will be weakened a little bit. And if the components are functions xj of variables t1 through tm, so every input here, every input is a function xj that can depend on other variables. And that is a function of m variables now. And again, we assume that these things have continuous partial derivatives. Then we want to compute the partial derivative of u with respect to ti, right? These inputs are being plugged into u, and so now u is no longer a function of x1 through xn, but of t1 through tm. And we want to find a partial derivative of u with respect to ti. Then that derivative will be the sum, j equals 1 to n, the sum over all the inputs xj, if you will, of partial u with respect to xj times partial of xj with respect to ti. So we keep the differentiation variable throughout, and we are just basically sort of like what you do in single variable calculus with Leibniz differentials, that you know that du dt is du dx dx dt. Well, here we have now multiple xj, and so you set up the same thing and you sum over everything. If you don't like summation notation, of course, it can also be written as du dx1, partial u with respect to x1 times partial x1 with respect to ti, plus partial u with respect to x2, partial x2 with respect to ti, plus and so on, all the way to partial u with respect to xn times partial of xn with respect to ti. Okay, so this is a formula. It is a large formula, but it is something that you definitely want to memorize. You want to internalize it, preferably in this fashion. After the proof and I think our first example, we're also going to take a look at another way to write down and remember the chain rule, and then we're going to keep going with more examples. So first of all, let's look at the proof. Now, proofs, as I've also said previously, aren't necessarily the main thing that we want to do in a first calculus class, but if we can understand where a rule comes from, we might as well go down that route. And so what I want us to do is I want us to realize that whether we have n variables or 2 variables, that is basically just a difference in notation. It makes things more complicated, certainly, and so we're just going to prove this for for a function of 2 variables, and those 2 input variables depend on t. And so, all right, so let me sort this out one more time. Dependence on t1 through tm is not that much of a problem because ultimately we differentiate with respect to a single ti. So that means if we hold the other tj's constant, then we basically have that we're working with functions of t or functions of ti as the inputs. The other part then, whether we have n input variables into our multivariable function or just 2 input variables as we have for this function f here, that makes this complication here, this computation here a bit more complicated. But we're just going to work our way through it here, and then we can also think about how this would work with more variables. So we want to take the limit as h goes to 0, f of x plus h, y of t plus h, minus f of x of t, y of t divided by h. Just like I said in the previous presentation, when all things fail, when we have nothing else that we can use as a tool, we will use difference quotients. And, well, now we need to somehow be able to reduce this to difference quotients for f and for x and for y. And so the trick that we do is we splice in an f of x of t and y plus h. And if you look at that, we just take the first one, subtract f of x of t, y plus h, add f of x of t, y plus h, and then we have the minus f of x of t, y of t here, and we still divide by h. I've just separated the fractions. So this is the same entity as before. Now what's the advantage? Well, all of a sudden here I can see that this is actually the difference quotient of a function that depends on h, if you will, where our base point is f of x of t, y of t, and then we just let h go we let t run from 0 to h as we plug it into the y. So that means we can apply the mean value theorem, and there must be a value c sub y between t and t plus h, so that the second difference quotient is equal to the partial derivative of f with respect to y at x of t, y of cy, y prime of cy. Because, like I said, if we hold the t now constant also, and just h is our variable, so our function is f of x of t, y of t plus something, then this is a difference quotient for that function, and that is now simply a chain rule of y of this plus h plugged into the other function. And so that means that our difference quotient in the back is the partial derivative of f with respect to y, f sub y of x of t, y of cy, times y prime of cy, right? It's, you take the derivative of the outside function, which would be the partial derivative of f with respect to y, and then you take the derivative of the inside function, which is just the y prime. On this one here, it gets a little bit more complicated, because here we have, of course, that h also. So here we have to be a bit more careful, but again, by the mean value theorem, for each h now, if we fix the h here, or if we do this for every h in particular, then this is something that goes from x of t to x of t plus h, and so that would mean that there is a cx between t and t plus h, so that that first difference quotient is equal to the partial derivative of f with respect to x at cx and y at t plus h times x prime of c sub x. And so that means we get the limit of f sub x, partial derivative of f with respect to x, x of cx, y of t plus h, x prime of cx, plus the partial derivative of f with respect to y, x of t, y of cy, y prime of cy. And now, well, now we use the continuity, because now cx is between t and t plus h, and cy is between t and t plus h. So when h goes to 0, cx goes to t, cy goes to t, and everything, and here's where we need that these partial derivatives of f as well as the derivatives of the inputs are continuous. If we let h go to 0, then everything goes to t, and we get partial derivative of f with respect to x at x of t, y of t, x prime of t, plus partial derivative with respect to y of f of x of t, y of t times y prime of t. And that is exactly the formula that we have in the theorem, except that we only have two input variables, x and y. And what do? We take our function, differentiate it with x, as well as with respect to y, and we multiply it with the corresponding derivatives of the inside, where the derivatives of the inside are not partials because we only have one input variable. The thing that becomes more complicated when you've got multiple input variables is that you really have to work with a difference quotient where you've got x1 of t plus h, x2 of t plus h, x3 of t plus h, and so on. So you have to splice in a whole lot more terms. You'll have a whole lot more arguments with the mean value theorem. But ultimately, the end result is the chain rule as it's been derived here. Okay, so now let's take a look at an example where we just do the computation. So if this proof was really, really hard on you, trust me, it's not as easy as it sounds when you talk your way through it. There's an awful lot of stuff in there that we don't typically refer to that much. And so let us just put that aside now. Let's accept that the result works, and let's see how it works. So let's take a function u of xy being the square root of x plus y, with input variables x of s and t being s squared plus t squared, and y of s and t being 2st. And we want to find the partial derivative of u with respect to s, and of course we're going to use the chain rule. So partial u with respect to x, well, that'll be the derivative of the square root function, or partial derivative with respect to x of square root x plus y, which gives us the derivative of the square root function, which is 1 over 2 times the square root of whatever is inside, which was x plus y here. And then, of course, we have times the derivative of the inside, and the partial with respect to x of the inside is 1. And, well, so that 1 I didn't write down here. And now we plug in x plus y, and so this is 1 over 2 times the square root. X is s squared plus t squared. That goes here. Y is 2st, and so that goes here. And of course, s squared plus t squared plus 2st is s plus t quantity squared. So this is 1 over 2 square root s plus t quantity squared, and that's 1 over 2 s plus t absolute value. We also need the partial derivative of u with respect to y. Well, that's the partial with respect to y of square root x plus y. Well, that goes the same way, right? The derivative of the square root function is 1 over 2 times the square root of what's inside. And then we multiply with the partial of x plus y with respect to y, which is 1, so that stays that way. So that's the same as that one. That doesn't always happen. It just abbreviates things for us here a little bit. But for the algebra, we get that this is also 1 over 2 s plus t absolute value, just like we did up here. Okay, so then we still need dx ds, or partial x with respect to s. Well, that's just going to be 2s, right? So d ds of s squared plus t squared, which is 2s. I guess I should have put parentheses around that. And then dy ds, or partial y with respect to s, that is partial with respect to s of 2st, and that'll be 2t. And, well, then, of course, the partial of u with respect to s is the partial of u with respect to x, times the partial of x with respect to s, plus the partial of u with respect to y, times the partial of y with respect to s. And really, this part is the most important part of the example. We just have to work our way through the chain rule like a mantra a couple of times. You keep your outer function, you keep your differentiation variable, and you just rotate the middle through all the input variables that your outer function has. And when you do that, well, you get du dx 1 over 2 s plus t absolute value times dx ds, which is 2s, plus 1 over 2 s plus t, which is du dy, times 2t, which is dy ds here, right? And so that ends up being s plus t over s plus t absolute value. And that is quite sensible if we're also realizing, and this is another example that is constructed to make us see a few things, and actually the example would have been easier if we had just plugged things in. That's, I think, the last example of that kind. And that is that if we plug x and y in, the function is just s plus t absolute value. And of course, s plus t absolute value, if you differentiate that with respect to s, the derivative will be 1 when s is greater than negative t. It'll be negative 1 when s is less than negative t, and it'll be undefined when s is equal to negative t. And that's exactly what this expression here gives us. Okay, so now a quick theorem where I just want to give you another way to formulate the chain rule. And that is, we take u to be this multivariable function so that all partial derivatives are 0 at the point A. I let r of t1 through tm be basically the input vector, x1 of t1 through tm, x2 of t1 through tm, all the way through xn of t1 through tm. And let that be a vector valued function so that u of r of t1 through tm is defined, and so that all the partial derivatives of the xi with respect to the tj are continuous at the point t1 through tm, for which we have that r of t1 through tm is a, so at the point where we want to ultimately differentiate. And then the partial derivative of u with respect to tj at that point r of t1 through tm is the vector that we obtain, let's write out the whole thing. It's the dot product of the vector we obtain if we take all the partials of u with respect to x1, x2, all the way through xn. And that vector will ultimately have practical relevance, so we definitely want to keep this in mind. So the dot product of this vector, which is also called the gradient often, might as well say the word, with the input vector, with the partial derivative of the input vector with respect to tj. So this is something that, as far as I can see, is most easy to remember the chain rule with, and we'll ultimately also write it down using the gradient vector itself. It's the gradient times the partial of the input with respect to tj. Now, let's say something very honestly real quick. That the chain rule is considered hard, and it is considered hard because over probably generations, teachers have observed that this rule is hard to keep track of for students, for people in general. And that makes sense because that rule involves a lot of variables, a lot of symbols, and the human mind can only keep track of a very finite number of symbols at the same time. Quantitative psychology has shown it's between 7 and 8 places or so. And so that means we need to find different ways to memorize the chain rule, and certainly then this formula is one way to memorize the chain rule. In your calculus book, and potentially also in your class, people will also show you certain kinds of tree diagrams to write down the chain rule. And I apologize if that's the way that really works for you. I've looked at it multiple times. I've thought about putting it into this presentation, but I just don't see how a tree diagram can help us remember a formula when in the end we really need the brute force symbolic connection to the formula. And so I'm not going to present that part. If that part works for you, by all means use it, but I'm going to stay here with symbolic stuff. Let's move on. So an example. Take u of xyz being xy plus z cubed, and let x of s and t be s cosine t, let y be s sine t, and you can see already I want to drop the arguments, and let z be t squared, and we want to find the partial of u with respect to t. Well, what do? We need to find this gradient vector, partial u with respect to x, partial u with respect to y, partial u with respect to z, which is nothing but the partial with respect to x of xy plus z cubed, partial with respect to y of xy plus z cubed, and the partial with respect to z of xy plus z cubed, which gives us y in the first component, x in the second component, and 3z squared in the third component, just like we see here. And of course now we still have to plug in what x, y, and z are, so that would be s sine of t in the first component, s cosine of t in the second component, and 3t to the fourth in the third component, and that's exactly what it is here. And then we need the partial of x, y, z with respect to t, so we need dx dt, dy dt, dz dt, which is the partial with respect to t of s cosine t, partial with respect to t of s sine t, and the partial with respect to t of t squared, which gives us negative s sine t, s cosine t, and 2t, right here. And now the chain rule, the partial of u with respect to t, the chain rule simply gives us that this is this gradient times the partial of the input with respect to t. And, well, that'll be, let's see, yeah, I first just wrote it down. So that's s sine t, s cosine t, 3t to the fourth from here, negative s sine t, s cosine t, 2t here. And that gives us negative s sine squared t, s squared cosine squared t, and 6t to the fifth. And that is the partial derivative. So I probably should have written down partial u with respect to t here, but that is it. Okay, so this is obviously why I like that formula. Like I said, it is involving quantities that we need to ultimately work with anyway, such as the gradient, or it involves quantities that in some ways we can quickly understand, because if we ignore that these are partial derivatives, then we already have taken derivatives of functions x, y, z when we talked about particle paths. And so that means that this ought to be hopefully reasonably easy to remember, and it keeps the symbolic character of the whole thing. Let's come now to the capstone of this presentation, and that is the idea of coordinate transformations. And that is where we need the chain rule in all its abstract glory. This is certainly a high-end example as well as a high-end problem if you have to do something like that. And the idea is fairly simple. If we have a function u that depends on the variables r and theta in polar coordinates, which, as we have also, as can happen, is often natural. If you are looking at a problem that has circular symmetry, then it is much more natural to state your functions in polar coordinates than in rectangular coordinates. Well, for such a function, I want to find the partial of u with respect to x as well as the second partial of u with respect to x, but only in terms of polar coordinates. And so here I need to give you a little bit of background because we haven't formulated these equations yet. The partial differential equations of theoretical physics, of mathematical physics, typically are stated in terms of Cartesian coordinates, in terms of rectangular coordinates. But that does not mean that the physics is native to Cartesian or rectangular coordinates. Physics is physics, and sometimes physics has to be expressed in polar coordinates, and then we may need to also want to solve these partial differential equations in polar coordinates. And we can only do that if the partial differential equation itself is stated in terms of polar coordinates. And that means we need to have a way to turn partial derivatives with respect to rectangular coordinates into expressions that involve partial derivatives with respect to the polar coordinates r and theta. And that's, of course, where the chain rule shines, because if I look at the partial of u with respect to x, well, if I know that u has variables r and theta that go between u and the rectangular coordinates, then I know that this is the partial of u with respect to r times the partial of r with respect to x, plus the partial of u with respect to theta times the partial of theta with respect to x. Same story as before, right? You keep your outer function, which remains your u, you keep your input variable, which is your x, and you take the middle and you rotate all the intermediate variables through in that middle partial and sum all of that up. Okay, so part of this works already because this is the partial derivatives of u and of theta. Of u are now in terms of r and theta, no longer in terms of x. We still need partial of r with respect to x and the partial of theta with respect to x, and we will need those ultimately in polar coordinates. Well, We know that the radius is the square root of x squared plus y squared. That means that the partial of the radius with respect to x is 1 over 2 square root x squared plus y squared, right? The derivative of the square root is 1 over 2 times the square root of what's inside, which is x squared plus y squared from right here. And then we need the partial derivative of the inside, and the partial derivative of the inside is 2x, which is what we have right here. We can simplify that, and we realize that, well, the 2's cancel, we keep the x. One of the things we recognize is square root of x squared plus y squared, well, that's r, so we might as well write that as r. And then we simply have to remember what x is in polar coordinates. X is r cosine theta, and r cosine theta over r is just cosine theta. All right, so this is pretty much a summary of the whole thing. We have a good bit more computation to go. But basically, you need to remember your chain rule, and then you need to take partial derivatives and turn them into the other coordinate system. Well, why not? All right, so theta, well, theta is the tangent inverse of y over x. Okay, sometimes we have to add pi, but that really doesn't matter when we take partial derivatives. So we can just leave that as is for the partial derivatives, and we realize that the partial of theta with respect to x, and therefore is the derivative of the arctangent, which is 1 over 1 plus the square of what's inside, so it's the square of y over x, times the derivative of what's inside with respect to x. Well, the y is a constant, the derivative of x to the negative 1 is negative x to the negative 2, and so that means we get times negative y over x squared. Well, if you multiply the denominator by x squared, you get x squared plus y squared. The numerator remains negative y. So we get negative y over x squared plus y squared. X squared plus y squared is r squared. Y is r sine theta. So you get negative r sine theta over r squared. And so this is negative sine theta over r. And therefore, the partial of u with respect to x is partial of u with respect to r times partial of r with respect to x, which is the cosine theta from here. Plus, well, okay, we have a minus here, so actually it's minus partial of u with respect to theta from here, partial of theta with respect to x, which is the sine theta over r that we see here, and which also gives us this minus sign. So I think this is where I can also see at a higher end problem why the chain rule is considered challenging, because we've got to take care of a bunch of variables, but at the same time, the more we get used to it, the easier this stuff will get. And note that I say easier, I'm not going to say easy, because it's sort of like certain kinds of workouts. If you train yourself to run 5 miles, it'll ultimately get easier, but 5 miles ultimately are still 5 miles. Okay, so that was, the problem isn't done yet, right? We actually want to have the second derivative of u with respect to x squared. And there's a good reason for that, because those second derivatives of u with respect to Cartesian input variables arise very frequently in the partial differential equations of mathematical physics. So we might as well work that out too. And we're going to actually use this result. And there's a little trick that, again, takes a little bit getting used to, which we're going to see on the next panel. Okay, so in order to get there, I also wanted us to simplify this a little bit. Well, I mean, what have I done? I've taken the cosine in the front, and I've taken the negative sine theta over r in the front, so that we have the partials in the back. That's preparation for the next panel, where we're going to use this as a differential operator, essentially. Because if we want to find the second derivative of u with respect to x, the second partial derivative of u with respect to x, that's basically the partial derivative with respect to x of the partial derivative of u with respect to x. And what we have seen on the previous panel, let me just go ahead and scroll back to that. What we have seen is that the partial derivative of function, anything, don't call it u, just call it function, partial derivative of any function with respect to x is equal to cosine theta partial derivative of function with respect to r minus sine theta over r times partial derivative of function with respect to theta. So in essence here we have written the differential operator, as these things are ultimately also called, the differential operator partial derivative with respect to x, in terms of the operators partial derivative with respect to r and partial derivative with respect to theta. So what we do here now is we apply the differential operator partial derivative with respect to x to the partial derivative of u with respect to x. So if I apply this operator, what I get is cosine theta partial with respect to r of what's inside minus sine theta over r partial with respect to theta of what's inside. That is the crucial step here to jump to the second derivative. You want to make friends with that and realize that in the computation on the previous panel, we could have, instead of u, just as easily plugged in partial u partial x and left it alone. It would have just looked a whole lot messier. Okay, well, now we continue, of course, and we know that partial u with respect to x, we have an expression for that, and that is we keep the cosine theta, we keep the partial with respect to r, and we know that partial u with respect to x is cosine theta partial u with respect to r minus sine theta over r partial u with respect to theta. So I've just plugged this one in, and we see that this continues with minus sine theta over r partial with respect to theta of partial u with respect to x, which is cosine theta partial u with respect to r, minus sine theta over r partial u with respect to theta. Okay, so we have succeeded in writing this in terms of polar coordinates. Of course, we'd like this to be a bit prettier than that, because here we still have to take partial derivatives of products, and that's normally not something that you want to have in a formula. So let's work things out. But basically, I could have put my rather infamous "the rest is just computation" blob right here, because from here on out, it's just the chain rule, not the chain rule, the product rule. So let's work this out though. This is cosine theta times, and the partial derivative with respect to r of cosine theta partial u with respect to r. Well, cosine theta doesn't depend on r, so the partial with respect to r of this is just cosine theta times the second partial of u with respect to r, just like we see here. Then we have minus, well here, this one depends on r, and this one depends on r also, because u depends on r and theta, right? So on these we can't drop anything. So we get minus derivative of the first with respect to r, which would be, because we've got sine theta r to -1, that'll be -1 sine theta r to -2, which is this thing, times the second one, which is partial u with respect to theta. Okay, good. And then we have minus the first one. Yeah, okay, so this would be plus. With this minus, it becomes minus. The first one times the derivative of the second one with respect to r, which is the second partial of u with respect to r, and theta. And yeah, that takes care of this term here. And so now we still have to take care of the other term. So we have minus sine theta over r. And now we take the theta partial of all this. Well, here this depends on theta, this depends on theta, this depends on theta, and that depends on theta. So we get the product rule twice. So what do we get? We get derivative of the first, negative sine theta, times the second partial u with respect to r, plus the first times the derivative of the second with respect to r, which is the second partial of u with respect to theta and r. And then we have minus. So we get minus and minus. We take the derivative of the first, which is cosine theta over r times the second. Then we've got plus, which becomes a minus from this one here. First one, sine theta over r times the derivative of the second with respect to theta, which is the second partial of u with respect to theta. And now all we can do is just multiply everything out. So we get cosine squared theta partial, second partial of u with respect to r. We get plus cosine theta sine theta over r squared times partial u with respect to theta, minus cosine theta sine theta over r, or sine theta cosine theta over r, second partial of u with respect to r and theta, plus sine squared theta over r partial u with respect to r, minus sine theta cosine theta over r times the second partial of u with respect to theta and r, plus sine theta cosine theta over r squared, putting these expressions together, partial u with respect to theta, plus sine squared theta over r squared, second partial of u with respect to theta squared. Let's pull this over to the next panel. That is the same expression as before. Now all we can do is really collect terms. So I think the first one I wanted to collect is the second partial with respect to r squared, and that's where we just get cosine squared theta second partial of u with respect to r squared, because none of the second partials of u are with respect to r except for with respect to r twice except for in the first term. Next one I wanted to collect, I think, a second partial of u with respect to r and theta, and that's where we see that this term here is the same as this term here, and it's not a minus and a plus, they actually combine, so we get minus 2 times sine theta cosine theta over r, second partial of u with respect to r and theta. Next one I wanted to collect is either the r or the theta. Let's just assume it's the theta. We see that these two are the same, right? So we get 2 sine theta cosine theta over r squared partial u with respect to theta. Next one to collect, I think, was the partial u with respect to r, and that's just plus sine squared theta over r partial u with respect to r, because there are no further terms like that. And finally, we have the second partial with respect to theta. So that's sine squared theta over r squared, second partial of u with respect to theta squared, and that's the answer. Okay, coming from single variable calculus, this is not a pretty answer. And in fact, even if you've done this for a while like I have, this is still not a pretty answer. So the beauty of these calculations, if there really is any beauty at all, lies in the fact that we can do the computation and that we can get a result. And potentially then also in the form of what you get when you take the second partial of u with respect to x and add to it the second partial of u with respect to y in polar coordinates, because this is an operator that has a lot of meaning in mathematical physics, and we will talk about that operator much later in this course. Also, it is meaningful in wave equations as well as in diffusion equations. It's called the two-dimensional Laplace operator, and so that kind of thing ultimately will, when you add those up, there will be a few terms canceling, not all of them, but ultimately you get something where you can solve certain equations of mathematical physics in polar coordinates, and you can then predict the behavior of certain kinds of wave phenomena as well as of heat propagation in certain geometries. And that is ultimately certainly always where we are headed. We are doing this mathematics to predict how reality ultimately behaves, and the power in the whole thing is that the mathematics predicts very accurately. Okay, so what have we had? We had a couple of examples. You need to internalize the chain rule, either by saying, okay, I keep my outer function and my differentiation variable the same, and in the middle I just differentiate with all the variables that go between the outer variable and the differentiation variable, and then I add all that stuff up. Or you can say that I compute that gradient, I compute all the partials of my outer function and multiply it with the partial of all the inputs, in the sense that we're taking a dot product. Or if that one doesn't work, by all means look at those tree diagrams that I mentioned that I just really have a hard time explaining with conviction, but which nonetheless, if they work for you, you want to use them. And so what lies ahead here for your homework is a bunch of computations. Have fun with them, get used to them, build that computational strength so that those computations don't trip you up as we proceed in the course. I'll see you when we talk about the gradient and about directional derivatives, and that's where we're going to use these computations to make everything conceptual again. All right, I'll see you there.